Thank you for letting me present today. And I just kind of wanted to give a shout out to my co-authors. So I have a lot of them, but especially Adam Kachansky and Carrie Kelly. So I really like this research because this research was kind of a product of this conference or a discussion that we had with Carrie Kelly last year. And so this is kind of the stuff that we kind of put together since our kind of preliminary discussions a little bit over a year ago. So yeah, kudos to this conference for getting people together and so on. So globally, wildfires are a major source of outdoor air pollution. And it's worth noting that poor air quality has been shown to result in roughly 3 million premature deaths per year across the globe. And it's expected that this is not going to get a whole lot better, especially as a result of wildfires. And so climate projections are suggesting that wildfires will just continue to get worse in the coming decades, with these trends being kind of driven by climate change, where you're getting earlier snow melt, especially up in the mountains. And so what this will do is this will prolong your wildfire season, and then you'll have hotter summers and so on. And so you can really kind of see this up in the image in the upper right, the MODIS satellite image, where you have not just one single fire plume, but you have multiple plumes. And so we're expecting to see more maybe images like this in the coming years. And so you can imagine that there's a lot of pollution that's going to be emitted by these fires. And so as a result, we're going to need modeling frameworks that can kind of forecast and kind of project the impacts of fire smoke. And this is kind of a tricky problem, though, because fire forecasting, so forecasting the fire growth and smoke modeling, they're kind of they're linked together. They're related in that you can't really make a forecast of smoke unless you're making at the same time a forecast for the fire growth, because your smoke emissions are going to be dependent on how large your fire is the next day. And so this is kind of a very tricky problem. And then kind of to add on to this is that fires are part of a very complex and kind of dynamic system where processes are going to be, at different scales are going to be kind of intricately linked together. And so this is not an easy phenomena to kind of model with a air quality forecast model or smoke modeling framework. The good news is numerical weather prediction models can now run at the scales needed to forecast fires in an operational setting. And there's a lot of different approaches that you can kind of deploy for forecasting wildfires and forecasting smoke. You have your more kind of traditional air quality, regional air quality models such as AirPact and HER, which simulates smoke a couple of days out. And then you have maybe kind of more local scale models that can kind of more focus in on the fire itself. And so you have, kind of coupled versus uncoupled models. And so a coupled fire atmosphere model is where you have an atmospheric model like WRF or some other kind of standard numerical weather prediction model, and you link that with a fire model. And so what happens here is a fire is linked with the atmosphere in that fire is going to be producing heat, and then that heat will then go into the atmosphere, and oftentimes that will result in your kind of wildfire plume rise that you often see with fires. There's also kind of local meteorology effects that fires can also have on the surrounding atmosphere. You can also have winds that get accelerated around the fire just due to the fact that you're adding this kind of heat source. And so as a result, what will happen is the winds around the fire will often accelerate. And so because the atmosphere is linked with the fire, you get this kind of positive feedback mechanism where these accelerated winds will actually cause your fire to grow larger more quickly. Thus, it'll accelerate the fire growth. And so research has shown that, coupling the fire model with the atmosphere is pretty important for accurately forecasting the fire growth in the future. And so a model that will be using the kind of forecast or project fire growth and smoke emissions is a model called the Warface Fire. And so all this is it's an atmospheric model, which is going to be, in this case, WRF, and it's coupled to a fire spread model, which we'll just refer to as S-Fire. And so just like any other kind of numerical weather prediction simulation, You have to have forecast boundary conditions, which will come from either, the HER, the NAM, the GFS. And then you'll also need to have information about your fuels and your terrain. So we use data from the Landfire satellite, which focuses on the continental US. And this provides fuel and topographic data at 30-meter resolution. Obviously, this does get resampled to a much kind of coarser grid. And then we also have surface dead fuel moisture observations. And then we kind of grid this up into onto a grid, which is also used to kind of initialize the fuel moisture model, which is used within Warface Fire. And then Warface Fire then gets kind of initialized off of these boundary conditions, and then you have kind of your fire and smoke simulation. And then the other thing that I should note too is there is an additional complexity of the fire is in that we don't exactly know where the fire is. The fire, we have MODIS hotspot detections, but it's difficult to kind of infer exactly where the fire line is. And so in this case, we used infrared fire perimeters to kind of initialize where the fire is burning, where the fire isn't burning, as you can see in the image on the left. And then areas where we have positive fire growth, we assume that those are the active fire lines, and we kind of initialize the fire off of those kind of active fire lines. So this is great, but how do we verify a modeling framework like this? For example, there's this kind of cartoon of this smoke plume right here. You can see that, normal air quality networks, the spacing between these sensors, in the case of Salt Lake Valley, the spacing is pretty good where, you have maybe sensors every 10 to 15 kilometers. But if you have a very fine scale kind of smoke plume, such as the one in this cartoon, these sensors really won't give you an idea of the exact shape of this smoke plume. And so because of that, we have to utilize other air quality sensors and networks. And so we're using Kerry Kelly's AQ and U network. And then we're also using mobile PM 2.5 measurements from the TRAX measurements, which has a light scattering sensor on board. We'll be using high quality data from the Utah Division of Air Quality to kind of validate the kind of low cost sensor network. And then we'll have semi-continuous mobile measurements made from TRAX. And then we'll have low cost sensor raw PM 2.5 concentrations that are adjusted using model specific correction factors for wildfire smoke. So if you want to know more about those correction factors, I implore you to ask Kerry Kelly about that, as there's a lot of work that went into that. So she can give you better details than I can about those kind of adjustments that were made. And so we looked at a case study from actually 2 years ago. So we looked at the Pole Creek and Bald Mountain fires. This was actually a pretty large fire. This was the largest fire, I think, in Utah during the 2018 wildfire season. And for us, this actually occurred pretty late in the season as well. This was actually in September. This case study was really interested in that the plume varied quite a bit over the course of the middle of September. We definitely saw a pretty pronounced kind of diurnal pattern in this smoke plume. And then at the same time, we were actually running operational Warface Fire forecasts for fire managers every 12 hours throughout the duration of the fire. And we were also generating smoke forecasts in addition to the fire forecasts, because there were a few field campaigns such as WeCan and BB Flux that were kind of ongoing during this time. So they're using some of the smoke output to kind of determine where to fly their measuring aircraft throughout this plume. And so first thing that we did is we kind of evaluated the low-cost sensor network. So just as a quick sanity check, so what we plotted up here, this is for a one-day period between the 14th and the 16th of September. And the markers that are shown here, these are just the different Utah Division of Air Quality sensors throughout the Salt Lake Valley. And then the black line is going to be the mean of all of the AQ and U low-cost sensors. And then the gray shaded area is going to be the standard deviation of those sensors. There's about, I think, 500 of those throughout the valley, so there's quite a bit of them. And then it's also worth noting that the Harriman site was particularly low relative to the other sensors, and we think that has to do with the fact that it was located in the southwestern corner of the valley. So I'll kind of go into that a little bit later. And so with this event, what we saw is we saw a big increase of smoke during the nighttime as a result of nighttime drainage flow, where we had this kind of interbasin exchange between Utah and the Salt Lake valleys. So kind of already saw this with Sebastian's work, different application, but nonetheless kind of same thing where, you know, we saw this kind of drainage flow from Utah into the Salt Lake valleys. And then during the daytime, we saw this kind of smoke kind of mix out. And this has to do with the fact that, you know, you have daytime heating, you have convective mixing, the fire is more active. And so this plume kind of gets lofted over the mountains and ejected off to the south or off to the northeast. And so what we did here is we actually just compared the nearest AQ and U sensors within half of a kilometer of the Utah Division of Air Quality sensors. And what you can see here is overall the agreement's pretty good. You know, you can see this really large spike, which the low-cost sensors seem to also capture in terms of the timing and the magnitude. So we saw this at Hawthorne, which is HWT. We also saw this at Rose Park. And we saw this at Copperview as well. So overall, the agreements between the low-cost sensors when they were calibrated and the Utah Division of Air Quality sites, overall the agreement was reasonably good, which is encouraging to see. And then if you do like a scatter plot of this, you can see that overall the agreement is pretty decent. So just kind of looking at the observations on a map. So what I've plotted up here is the low-cost sensor observations as colored dots. And then I've also plotted up the fire perimeters, which is going to be the red area. And then the tracks observations are going to be plotted up as this red line, or not this red line, but this colored elevated line that goes kind of throughout the middle of the Salt Lake Valley. This is the tracks red line. And so we can see is there's a lot of structure to this smoke plume where that the PM 2.5 concentrations are kind of centered more, are concentrated, or the higher concentrations are kind of centered in the middle of the valley. And then on the edges of the valley, you see much lower PM 2.5 concentrations. And so we suspect what's going on here is that you're getting kind of this drainage flow or down valley or down canyon wind flows coming off of our mountain ranges, which is kind of pushing the smoke off of the benches of the valley into the middle of the Salt Lake Valley. And in addition to that, you also have this kind of larger scale kind of down valley flow or interbasin exchange between the Utah and the Salt Lake valleys, where this is propagating smoke from the Pole Creek and Bald Mountain fires down through the Salt Lake Valley and eventually off into the Great Salt Lake. And so we kind of have this kind of complex interplay between different mountain valley circulations that are kind of at different scales. And then if you look at the model or Warface Fire simulations, surprising, or not surprisingly, but you know, we're really encouraged to see that, you know, we're also capturing this gradient within our Warface Fire model simulations where we were seeing lower concentrations, especially near the mouth of Emigration Canyon, which is indicating that you're kind of filtering in this kind of cleaner air from the upper elevations down into the valley. So this is acting to kind of clean out or lower the PM 2.5 concentrations within the valley. And overall, you know, and you can also see that on kind of the western side of the valley too, you know, by the Harriman site. So that's probably why the Harriman site in the Utah Division of Air Quality measurements, why that was a lot lower relative to the other stations, because it was located in the periphery of the valley where there was probably some drainage flow. And so overall, when you compare the modeled smoke plume with the modeled smoke plume according to the observations, and so I kind of drew that as this white dashed line, you can see that overall the agreement's pretty good. But you know, it's worth noting that especially on the eastern side of the valley, maybe this agreement isn't as good, especially near the mouths of Big Cottonwood and Little Cottonwood canyons. The gradient isn't as well captured by the model. And I suspect this has to do with the model resolution. This resolution was at roughly 1 kilometer resolution. And I think what's going on here is the WRF atmospheric model is just not able to resolve the meteorology associated with these very fine scale kind of canyon winds. So that's kind of worth noting. We also kind of just ran a variogram analysis very quickly in the observations just to see, what kind of resolution model do you need to kind of resolve the this smoke plume. And in this case, we need to roughly have an effective model resolution of about 7 kilometers to kind of resolve local scale smoke plumes just based on this one case study. But obviously we'd have to apply this to a lot of different case studies to get a kind of more refined number. And so if you assume that the effective model resolution follows the rule of 5dx, with dx being your grid spacing, you would probably need some type of model grid spacing that should be between 1 to 2 kilometers, which we're using for the atmospheric grid over the Salt Lake Valley. And so while the Warface Fire simulations did a reasonable job capturing the timing and the shape of the smoke plume, it's worth noting that the smoke concentrations were overestimated for the Salt Lake Valley, where if you look at the observations, which is on the panel on the left, you can see that the mean concentrations kind of peaked at around 40 micrograms per meter cubed. But if you look at 2 different model simulations, one where we constrained the model simulations based on the infrared fire perimeters, and one where we kind of just let the model kind of drive the fire growth with the wharf winds, you can see that there was a pretty pronounced kind of overestimation in wind or in PM 2.5 concentrations during this period of time. And so we think that this issue is potentially related to the drainage flow, especially coming out of Spanish Fork Canyon, where the winds were definitely kind of overestimated that. And so what we think was going on is this drainage flow is kind of pushing the smoke into the Utah Valley and then into the Salt Lake Valley too quickly. And so because of that, we have this kind of earlier kind of peak in PM 2.5 in the model simulations that we don't see in the observations. And then you'll notice that even the constrained run in the forecast simulation, we do have this kind of overestimation of smoke, especially in the forecast simulation. And we think this is actually related to the fire growth, where you can see that the Bald Mountain fire after 2 days is really kind of being over predicted by the model. And this might actually have to do with the fact that the model is just not able to capture fire suppression. There was some risk of the Bald Mountain fire kind of pushing into part of the valley. And so there's a lot of fire suppression efforts to kind of keep that fire out of the valley. And so because of that, those fire suppression efforts, the fire never actually went into the valley. And so because of that, in the model, since we can't capture those effects, we have these kind of overestimated smoke concentrations as a result. And so just to kind of summarize here, the low-cost sensors appear to be useful tools for resolving the spatial temporal heterogeneity of wildfire smoke plumes. But it's worth noting that these sensors should be used in conjunction with higher quality kind of FRM, FEM stations. Mobile measurement platforms also appear to be effective for depicting smoke plumes. The only downside of this is a very unique network that you really don't see anywhere else in the US. So I don't know if this could be used on a large scale unless we get more money to apply this on other kind of light rail systems. And then low-cost sensors are really effective tools for validating smoke transport models, just kind of based on this case study. And it really kind of helped identify the strengths and weaknesses of our smoke modeling framework. And so that's all I have for today. So, yeah, we're excited to kind of continue this work. We did get funding going into the next year to kind of look at this, but looking at ozone. So I'm really excited to kind of apply this to ozone.